Okay, hi everyone. Thank you for choosing this talk. I have to say, after a whole day of conference talks, you're choosing a talk about complexity and hardware acceleration. And I have a horrible jet lag, so good luck to us all. Maybe it will work. One thing that I learned when I wrote this slide deck is I use a lot of ChatGPT imaging, and ChatGPT really likes cups. In all the images, it puts a cup and writes something on the cup. It's amazing. It's like he knows that programmers just like coffee and horrible things. So we will get to that. Few words about myself. I'm a system engineer with more than 20 years of system programming. I'm very active on LinkedIn where I talk about performance, C++, and other stuff. You can visit there. I have my own blog post site. It's called CPP Next, where I delve into these problems in a more important way, like you cannot do everything on LinkedIn. And I have a YouTube channel. I kinda didn't update it in a long time, but I'm planning to start updating it again. A lot of work. So let's start with a story. I want you to imagine yourself as someone that just got out from school. You're fresh from the university, you're at your first job, and by luck, your team leader is amazing. He wants you to learn. Not a lot of people do that. So he gives you very important tasks, and you start looking at the code, and you found something horrible in the code. There's one function that works in quadratic time. Horrible. You run to your team lead and you're telling him, hey, it works in quadratic time. We can do much better. This is an amazing place to work in. We cannot do something like that. At school, they taught us that quadratic time is horrible. So the team lead tells you, fine, go do that, and smile. You go all algorithm mode, you take the whiteboard, you take the markers, start writing the algorithm, grinding it until you do something, you spend days, but in the end, you got n log n big O complexity. And you're happy, you're saying, yes, I did it. I spent my time well. But did you spend your time well? We didn't benchmark our code. So we are happy to write the benchmark, and we are happy to start running it. And then the horrible things happen. You run the benchmark, and the previous code is much faster than the code that you wrote. But how can it be? Am I a failure? Didn't I understand anything from school? No, you're not a failure. Everything that fails, it's an opportunity to get better. You need to understand that if something failed, there's a reason for that. And this talk gonna talk about exactly that. Why is this a misconception? Why big O notation is not the most important thing? And it all starts in universities. When they teach us that algorithms are isolated beasts, they run in the cloud. Nothing interferes with it. Everything is good. And if you were lucky, you've done some computer engineering courses. In computer engineering courses, they teach you how CPUs work, how memory works. But no one connects the dots for you and tells you, hey, algorithms run on CPUs. You need to know how those things work. And yes, Pierre, you need to know your CPU. And by the way, I'm showing recursion here. So we are in 2026. I'm showing a slide from 2025, where Pierre is showing a slide of me from 2024. And next year, Pierre, I want another recursion. So let's talk about complexity. What is complexity? When we got to school, the first course we did was Introduction to Computer Science. And already in Introduction to Computer Science, we started to understand, hey, there are complexity classes. And we want complexity to be as low as possible. So we know that constant complexity is good, linear complexity is meh, and polynomial complexity or exponential complexity is really bad. A square complexity is horrible, and if you even think about writing something in the power of 3, you go to jail. Like the police comes in the moment and take you away. But how do we calculate those things? So in big O notation rules, each operation has a cost of 1. No matter what it does, it has a cost of 1. If you have a loop and the loop runs for n times, you pay n times 1. That means this is linear complexity where we have big O notation of n. This is logarithmic complexity where we are multiplying I by 2 all the time, and that means we're growing exponentially, and that means we will run less time. And this is logarithmic. If we have quadratic, or even worse than that, that means that we have nested loops. So the nested loop runs for n times, and the outer loop runs for n times. Then we just multiply them, and we get n squared. If we will combine everything together, we have all the complexities here. But big O notation says that your algorithm runs as good as your worst part of the algorithm. That means if we combine everything together, we still get O(n squared). So those are the simple rules. But if we will look at the simple rules and we try to understand something before we continue and delve into this talk, we can look at this simple functionality. So we have sum that runs linearly on an array that is on a stack, and we have something that runs logarithmically, but the name of the function already tells us something. So if we will think about it, just by theory, we will say the logarithmic function is much better because it's logarithmic time. But not always. Do something heavy, let's say it even runs in constant time. But running in constant time says nothing. You may have a lot of operations that take a lot of your CPU, like going into the memory all the time. And actually, the logarithmic function may run slower than the linear function, even though if by theory, the linear function is slower. This is the basic complexity. After we finished the basic courses, we started data structures. So we need to understand how data structures work. And this is basically a table that looks almost on all data structure and how the complexity for these data structures work, how they are built. And the most important line here is the binary search tree. So binary search tree, we learned that everything is log n, everything is fine, everything is great. But binary search tree works in average complexity. That means a binary search tree can be so unbalanced that it will be just a linked list. And then you write, then you will have a complexity of O(n). So complexity lies to us. Already here we can see that complexity lies to us a little bit. And I want to show you a simple problem that I love asking during interviews that I'm conducting with people. And this simple problem makes people just go lost in the solution. And when you will see the solution, you will understand it's really simple. So what you need to do here is just create a function that receives two vectors, that treats the vectors as if they are groups of numbers, and it's subtracting one group from the other. What does it mean? This is an example. We have large A, and we have B with 2 and 3. Our result is just the same order of A without the appearances of 2 and 3. Simple. So the first solution that comes in mind is the naive solution that says, let's run on A, then let's run on B. We will see if one of the elements of B is the element that we are checking in A. And if it's one of the elements, we will just break because we want to make better algorithm. And then if we actually didn't find it, then we're pushing it back. So this is great. This is the first solution. I'm really happy when people get to it. But then I tell them, hey, we can do it better. We can do it in linear time. Can you think of a way to do it in a linear time? And most of the people cannot answer that. But this is that simple. So basically, an ordered set is a hash table. Hash table, we already know that it works in an amortized time. Remember that word, amortized is evil. And we will just copy everything to an unordered set. We will run on A. we will use the knowledge that we have that this set, or basically hash table, works in a constant complexity, and we are basically just running on A. So here the complexity is OM plus ON, and the larger one just wins. Still, it's linear. Everything is fine here. It wouldn't be my slides if I wouldn't show you something more modern. So here we have the same solution with ranges. In my opinion, it looks much better. But I love functional code. You need to understand it. I know that when people will start looking at the YouTube, they will say, this is ugly and horrible. How can you write something like that? I disagree. Come find me. Algorithms. Now, we know everything about all the data sets. We're carrying everything, this knowledge with us in the university all the time, and it's heavy on our backs, but we still need it. And then we get to algorithm course. And in algorithms, it starts to get even heavier. Now we need to understand the science behind graph theorem. Now we need to reduce problems. Now we need to use all the data structures that we used before to understand how we can do these algorithms on data graphs better. And one of the best things to show is how we used to calculate the complexity for Dijkstra. Dijkstra is basically a very simple but very important algorithm that takes one vertex and calculates all the shortest paths to all other vertices in the graph. It's doing it by going all over the neighbors, pushing them into a stack, putting, not a stack, to a max heap, mean heap, sorry, to a mean heap, and then relaxing the edges. Basically, you can read about it later. But how did we calculate the solution here? The complexity for it is already a beast. So we started with a vector. We need to initialize all the vector. The complexity of initializing one cell in the vector is O1. We run for all vertices, and that's OV. We have to extract a minimal node. Minimal node from a heap. We need to reheapify it, so it's log n. And we run it for V nodes, so it's V log V. Then we have to relax the edges. Basically, relaxing the edges is running on all the edges and changing the weights. We run with O1 on all edges. It's E, so it's O of E. And then we have to decrease the key and change the heap itself. It's O log V, and we have to run it on all the edges. So it's E log V, and basically, I want to shoot myself. Now we have a lot of books, and we are carrying those books with us to all the tests, and we are getting a lot of, we don't get any slack. You have to have the best big O notation. What will you do if your big O notation is bad? Your algorithm will run really slow. So we're carrying everything with us, and this is a pain. I remember myself in the university. I loved learning, but it was a pain. Now let's talk about amortized time. Amortized is an invention of humans. We just said, hey, some things run slower than we say. Let's invent something that will say it runs faster. So a very good example for that is a vector. You know, when you push to a vector, it may reallocate. If a vector reallocates, it needs to copy all the data from the old location and add the new variable. The capacity of the vector grows by 2. That means we are growing exponentially. And to understand that, like, think about it. It's not constant anymore. You need to copy. So why do we still say that, hey, pushing into a vector is constant time? Because we invented amortized. And by inventing amortized, we are saying, we are not just pushing something and calculating if it needs to copy something. We have potential functions, just like in physics. We are computer scientists, we are mathematicians. We have potentials as well. And to understand how this potential works, it has a cost function. Basically, we're saying, if we need to push something into a vector, if we do not reallocate, that works in 1. We pay 1 for that. And if we need to reallocate, we pay 1 for the push that we are doing right now and the old size that we had to copy. The potential function is basically 2 of the size that we have right now minus the capacity of the vector that we have right now. This potential function is just telling us that, hey, we grow it so much that our potential is it's not positive. So we spent some work and we already paid for it. So we don't have to pay for it again. And the amortized cost is basically the cost that we're paying right now, plus the potential. Let's look at the no reallocation case. So in no reallocation, we had S, the size becomes S plus 1, the capacity stays the same, the cost is 1, as we said. If we assign all the values into the potential function, we get 3, constant time, everything is good. Now let's look at a reallocation case. So we have S becomes S plus 1, just as before. But capacity is multiplied by 2. And we pay S plus 1 for the cost function. If we assign all the values to this cost function, we will get 3 again. How great is that? Everything is constant. But don't forget, it's constant in theory. Still, when you're writing code with vector and your vector might reallocate, you will pay for it in runtime. So you need to take all these things into your account. You cannot just say, it runs in O1. Everything is constant. I will be fine. No. And we will get to more examples like that. So now that we understand how things were calculated and that we invented a lot of stuff, where did it start? Who knows who this is? Turing. This is the guy that we have to say thank you for computer science and for winning World War II. So he invented something that's called the Turing machine. Turing machine is something pretty simple. It's basically a long tape, endless memory. We have rules, and we have a head that reads each one of the cells inside the machine. Pretty basic. But this machine was invented to show that something can be calculated. Something can be halted. Something can stop. So if we know that we can write an algorithm on this machine, we know that it's something that will work and it's something that we can calculate. But calculating something is not enough. We need something to run fast. So we invented something that's called classes, complexity classes. The first class and the class that everyone liked is the class called P, polynomial time. That means we can solve a problem in a polynomial time. Polynomial time, it's all our friends. Even quadratic is a polynomial time, and it's still in a good company. So some of the algorithms that do it in polynomial time is sorting. The algorithm is pretty finite. And pathfinding, I already showed you Dijkstra. This is exactly pathfinding. It works in polynomial time. And then we have NP. NP means that we can verify that the problem can be solved in polynomial time. And by the way, NP is not polynomial. NP means not deterministic polynomial time. And this is one of the worst names in computer science because people just think it's not polynomial. It's not. And examples for that are Sudoku, traversal salesmen. We know that traversal salesman is a very hard problem. And 3-SAT is a very important problem that is NP complete. That means all other problems can be NP if they look like 3-SAT. So let's talk about Sudoku. Who thinks that solving Sudoku is easy? One person. Sudoku is not easy. But if I will give you the solution for the Sudoku, will it be easy for you to verify that it's the correct solution? Yes. We will just run on all rows and all columns. We will verify that everything is good. And we will go on all the Sudoku chunks, and we will see we have all the numbers. So it does it in polynomial time. And this is the first step of showing that something works that something is inside an NP class. So we verified that. Then we want to show that basically Sudoku is an NP hard problem. It's really hard, not just for us to solve it, but for computers as well. And to do that, we need to show that we can reduce the Sudoku problem into a 3-SAT problem. Because 3-SAT is already NP complete, we can say that if Sudoku can be represented by 3-SAT and 3-SAT will be solved, then the Sudoku problem will be solved as well. 3-SAT is basically clauses of 3 Boolean variables that has or between them and between all the variables. And a three-sat solution is satisfied only if it's true. That means that all the variables needs to be true in the end. So how do we start? We define variables. This is Boolean algebra. That means that all our variables can be true or false. That's it. We have clauses and we have variables. So we send the variable to all clauses that it needs to be sent to, and we can send it as the direct value, or we can send it as an invert value. That means if something was true, it will be false. Then we define clauses. Clauses have three variables inside them, as I said, and each clause will represent a number in Sudoku, not just a clause in three-sat, a number in Sudoku as well. Then we will build the grid of the Sudoku with all those clauses in a way that we will get true in all the clauses. And if we get true in all the clauses and all the numbers that are represented by the clauses are good, basically we can say we solved the three-sat problem and we solved the Sudoku problem. This is really just a taste of how to do that. And if you want to go and learn how to do it or remind yourself how to do those things, there are great YouTube videos that show exactly how to solve those things. But basically this section, I wanted to show you the pain that we have to bear just to keep up with big O notation. We have to know all the classes. We have to understand reduction. We have to do optimal complexity. But no one told us that optimal complexity is not always the answer. We cannot just look at it as the answer for everything. And the most important part here is that practice and theory are different things. In real life and in practice, you have CPUs, you have different hardware. Each hardware works in a different way. And by the way, there's a coffee bun. So we need to understand how our hardware works before we start writing our algorithm. We need to understand not just how our hardware works, what is our workflow to write the algorithm in the correct way. So let's start with CPU evolution. It's all started with ODC 2001, Space ODC 2001. Basically, humanity was so afraid of IBM that they wrote books about it. And the robot there, or the AI, was called HAL. HAL is basically IBM. And today, 60 years later, if I put this little crown on them, people are afraid of computers. It's the same thing, but the bots are still our friends, so let's use them for good. But it started with von Neumann. Von Neumann was a mathematician, and in the 30s, he defined something that looks like a CPU. It has a control unit, it has arithmetical and logical unit, it has inputs and outputs, and it has a memory. The fun part is, this solution was introduced in the 30s, and still most of your CPUs use the same solution. 90% of your CPU use this solution. If we will look at very simple modern CPU, very simple. It's not like our CPUs actually look like now, but we still have inputs and outputs. We have the logic units, we have main memory, but we have better buses. We have buses for control and for data flow, and we have registers. Basically, it's a von Neumann machine. But the von Neumann machine works with one instruction at a time. That means our output of instructions or our calculations are really bad. And that's why we needed to add something that's called a pipe. So most modern CPU has a pipe. This pipe is very old. It has only 4 stages, but it's really good to just understand. So we can work on 4 instructions in the same time. And if we work on those 4 instructions at the same time, that means that our bandwidth is much, much better. Modern CPU has much wider pipes with more execution units, and even some CPU has double pipes and triple pipes. That's not good enough. Why? Because if something gets into a pipe and one of the units needs to stall, I mentioned that if we are accessing the memory, the unit will start stalling. And if we have other instructions in here, they will be just stalled for no reason. Why no reason? Because nothing actually is used from the memory that is actually written to in this example. So that's why something that's called out-of-order execution was invented. That means that if we don't have data hazards, we don't use the same data that we read into a memory, and now we have to read from the memory, the same memory. We can reorder everything. We can just push it to the reorder machine inside the CPU. We can calculate it in the same time and commit it when it's needed. So we are not losing time here. And it's actually made the CPUs much, much faster, but it's harder to reason because everything is not working exactly as you think. So your compiler created the code for you, but it's not the code that's running on your CPU. The code will be reordered twice. That's not enough. I mentioned pipe instructions. So memory is a very easy pipe instruction. We understand we need to go to the memory. It takes time. We will have latency. We will have something to push back. But it's not the only instruction. We have to understand that other instructions, other ALU and FPU units have different codes. So add has one cycle. It's the most basic instruction. IMU is basic integer multiplication has 3 cycles. Division is 20 times slower than that. And it depends on the architecture. It might be even slower than that. And by the way, there are even less of those units inside your FPU, well, inside your CPU. Basically, FPUs, you have less FPUs than ALUs, and you have less things that work on doubles. So you need to understand that as well. It's not just that it stalls more, you have less of those. So your CPU cannot just produce more of those. And to understand that, here's a really simple example. We have 2 functions here. One function is dividing by 100 to get 1%. The other function is multiplying by 0.001. Basically, the result is the same. But if we will look at the benchmark, multiplication is almost 2 times faster than division. And already in this small thing, if you need micro optimizations, you can already start thinking about these things. Your algorithms will run faster if you can do something with multiplication instead of using division. I know that using div is much easier to understand, but sometimes you need speed. That doesn't work just for FPUs. That works for ALUs as well. So here we have an example with divide by 2 on integers and shift right by 2. Again, the logic is exactly the same. Dividing by 2 is exactly the same as shifting right, by 1. Exactly the same. But again, if we will do the benchmarking, we will get that shift right is faster than the division in integers as well. Why? Because shift left and shift right are basic instructions in all the CPUs, and the CPU know how to execute it much faster than division and multiplication. The good news are that the compiler knows and sees your code, and for shifting, it already does the job for you. So you don't have to think about it all the time. And if you want to know more about it, I had a whole talk about int or uint, where I show how the CPU treats those things and why sometimes you need to use one and not the other. Branch predictions. So branching is something that is really, really traumatic for your CPU. Basically, when you need to branch, you need to calculate something. You stall everything. Now, nothing works because I need to calculate if I need to branch to taken or not taken. And only then I branch. And by the way, branching is really, really hard for the CPU as well. It needs to go to a different basic block. It needs to load different things. And it needs to propagate registers. That's a lot of work. So to make this a little bit better, branch prediction was added. Branch prediction says, I will speculate if I was taken or not taken. And that means that we know that, that we can basically save time when we are running something because our CPU says, oh, I know that this branch is usually taken. That's why I will start just calculating it and everything will be fine. Of course, if it was mistaken or taken not correctly, we will have to recalculate everything and flush our pipes, but it still saves a lot of time. This is a very simple example of a branch predictor with 2 bytes. This is one of the first branch predictors that was actually used in CPUs. And it was starting with strongly non-taken, and then it would just have a state machine and understanding if this instruction, this branch needs to be taken or not. SIMD. is another good tool that we have right now in modern CPUs. So here I'm showing AVX 256. We have 8 floats, and sometimes we can just use vectorized instructions to do our work, the work for us. Here we're using 8 FPUs, floating points, and we can calculate them in one instruction because we have vectorized units inside our CPUs. Most modern CPU has those different vectorization units, and the ones that are actually useful are AVX and AVX 512, in my opinion. And the best thing is, the good news basically, before the C++ 226, we had to know each one of our CPUs that we are using and use very low level code to do SIMD. Right now, with C++ 26, we finally have the ability to do it from the standard. The standard will do the heavy lifting for you. The only thing that you have to understand here is that to do that, we need to copy it to a SIMD vector, and then to copy it from a SIMD vector. That means that you have an overhead. And you need to understand before using a SIMD, can you pay for this overhead? Because using a SIMD, it's not always the right thing to do. Same thing about GPUs. When you write for GPU code, it's not always the best solution. Even though it can run really fast, the PCI Express is really, really bad. Branchless program. So I said we have a branch prediction. But our friend, the GPU, is made of many, many, many small CPUs that all the cool parts were taken from it. That means all the cool units like branch prediction and everything was just taken away. And it's really traumatic for the GPU to see branches. So we can use something that's called branchless or branchless calculations, branchless computing. And that means we are removing all the branches. We prefer to calculate everything, but remove the branches from it. In this example, for CPU code, it's really easy. You can see that we have a branch for 4. We're branching in a loop. Then we're saying if a number is positive, we're multiplying it by 2. If it's negative, we're making it positive. For regular CPU, that's fine. We have branch predictors. It will run good. But when you write for something that is a SIMD and you have a lot of vectors or a GPU, you prefer just to calculate everything in the same time. So here we are calculating both things, and then we are using trinary operator to set them into the output. Now you might say, hey, trinary operator is a branch. And no, it's not. For modern compilers, and especially for compilers for GPU, it is lowered to something that's called select. And select is a basic instruction inside the CPUs there that is done in one cycle. So it's better sometimes, even for our CPU and not GPU, to use trinary operator. Cache. Cache is one of the super important things for your calculation and algorithm runtime. So all the data starts inside the disk. Disk is huge and slow. Even though it's NVMe, it's still slow. We want to bring our data as close as possible to the CPU. The closest is to the CPU, the less memory we have, and that means we need to manipulate it in a better way all the time. But if we can keep it in L1 and L2 caches, that means that our runtime will be much, much better. And what we want to do is make our programs as cache-friendly as possible. But we don't, as I mentioned, we don't have all the space in the world, and we have to evacuate lines from the cache. Usually, the caches are using something that's called LRU, least recently used. And here we have an example of least recently used. Basically, the most unused value from the cache will be evacuated to bring a new one. So we're starting with a cache with 7 in it. Then we try to bring 0. 0 is in the memory, not in the cache. We have a miss, we are bringing it into the cache. Then we are bringing 1, same thing. Then we are bringing 2. We need to evacuate. 7 is evacuated. Then we are using 0. 0 inside the cache. 0 becomes the most recently used variable. And then we're using 3, etc. We need to evacuate. And that's how it works. Most caches work with this algorithm. All good and dandy, but even in school, we learned that if we use threads, things will just get better. We will throw everything on the threads, and it will run faster. Well, let's look at a system that's an old system that is multi-thread system. Multi-thread system means that we have one core and many threads and no cache. In this situation, when you start, and it depends on your workload. Everything depends on your workload. So in this case, we are starting and we are adding more threads. These threads are actually making your program faster. Then we are hitting a wall because adding more threads is adding more overhead, and it doesn't help you with your calculation, but it doesn't end there. If you will add more and more threads, the overhead of context switching will be so bad that your performance will just go down. But that's an old system. Most of our CPUs right now are multi-core and have caches. And this is a really interesting graph, and I really like it, because here with caches and cores, you have exponential performance enhancement. But then you have a valley. Why do you think the valley happens? Cache misses. Basically, the more cores that you add, the more cache they need, and they're garbaging each other cache. And that means you have more misses, and you need to bring more memory, and you need to evacuate more, and that means you get to a valley. So if you got to a valley, to get out of the valley, you need to add more and more threads. So the cache is not in the game anymore. And if the cache is not in the game anymore, and we're adding more and more threads, we're becoming multi-thread, like the old CPU. We don't want to get there, because it will fail really, really fast. And if you would like to read the paper for that explains all those things, I prepared it for you, so you can read it afterwards. And here's a practical example. We have a vector with 10 million members. 10 million members. We use accumulate on a single thread to do summary of that. And then we use reduce with par. In C++ 17, we have added something that's used par. That means that we have parallel execution, and we're using it on the same vector. And if we look at the benchmark of that, we can see that the single thread is better than the parallel. Why is it better? Because on a single thread, you have linearity. You don't need to split it to other vectors. You don't need to split it to other threads. You don't have overhead for context switching. SIMD kicks in much faster from the compiler, and it works much, much faster, even on one thread with 10 million units that we calculated. But you might say, yeah, you used par. Par is bad. Use par and sequence. Par and sequence means that basically we will use more SIMD if we can, and we will not lock, we will use atomics, and we will do a lot of hoops and do good stuff, and it still works. The good news are, this is with 100 million units, it's becoming better. So maybe if I will have more than that, the parallel and sec will get better. But the parallel itself is just getting worse and worse. Okay, now let's get back to the first thing that I showed you. I showed you the group subtraction and how we worked with that. So here you can see, because the first thing that I ran here, the B vector was small enough to get into the cache line, naive solution that run in quadratic time is much faster than the other fancy solutions. But if B will get big enough to not be inside the cache, and we will have to evacuate it all the time, we will get the set solution is much better here. But I haven't shown you a cache-friendly algorithm for that. I can write a cache-friendly algorithm for that in n log n that will beat all the other solutions all the time. And we will finish with histograms, an example that will explain again about the caches and how those things work. So histogram is a very important statistical function that says we have bins and how many times something appears in these bins. So here, if we will look at the first bin, we have 5 numbers between 0 and 5 in our vector that appeared in this, and we have 5 of those in this bin. The first thing that comes to mind, again, when you're implementing something like that is hash table. We want to access something fast. Hash table has bins already. It's something that it's really easy to implement. And as you can see here, we have 64 bins, And 64 is a very important number because my CPU has 64 byte lines. So I want to make it as hash friendly as possible, cache friendly as possible. And we are replacing and running it with div. Div is basically calculating everything into the bins. But when we think about it, we can implement it with a vector as well. So the code looks almost the same, but the performance is different. Just because we use vector and not unordered map, we got much better performance. Almost 4 times as faster than the unordered map. And why does it work that way? Let's say that we have a couple of values inside the heap. Heap is your memory. And our system has only 2 lines of 32 bytes cache. When you implement an ordered map or a hash table, linearity is not something that promised to you. So if you want to bring something into the cache line, the CPU doesn't bring just the 8 bytes into the cache line. It brings all 32 bytes. And if your bytes are not linearized, that means it will bring garbage into the cache. And if we have just 2 lines, that means we have 2 lines and that's it. And our hash table is much bigger. That means that we will have to evacuate from L1 and do it again and again, and we will lose in this fight. But if we will look at vector, vector is already something that's defined to be linearized. If it's linearized, that means that the CPU, when it touches something inside the vector, it brings all the 32 bytes into the cache line. That means in this case, we brought all the data into one cache line, and that's it. The data is inside the cache line. It's always hot, and it's there to stay. And that's why when we are using things that are cache friendly and things that we calculate correctly and understand how those hardware that we are using works, we will get much, much better performance. And now with all this knowledge and all this power and all these dots that are connected, that big O notation is good, but things are not isolated. You run on your CPU. Maybe your algorithm will run great on x86, but when you go to ARM, it will run much worse because ARM works in a different way, and you will need to do different optimizations there. You need to understand how your CPU works. You need to understand how the hardware works, and this will make you better computer engineers and software engineers. Thank you.